All right, we're going to pick up where we left off last time here, talking about these aldol addition and condensation reactions. All right, remember that this is when we take an aldehyde or ketone and we add in some sodium hydroxide, some base, and we get a reaction between those two aldehydes or ketone molecules. Typically, this would just be written not with both of those there, right? Just the one, showing you our chemical equation. I think it's helpful to draw on the other one so we can see how these things get connected. Importantly, we're going to be connecting the alpha carbon of one to the carbonyl carbon of its neighbor, right? That's how we got our aldol product here, okay? Specifically, if we look at the reaction, what we learned about these alpha carbons is that that alpha hydrogen is relatively acidic, so that base can pull off that alpha hydrogen to create our nucleophile, our enolate ion. All right? Our nucleophile attacks that electrophilic carbonyl carbon, creating an alkoxide that we then protonate, so we get what we call an aldol product. We got an alcohol group and an aldehyde group in that same molecule. And we said that we can sort of have an easy double check here to make sure that everything's connected correctly at the end. First of all, counting carbons, but also counting from our carbonyl carbon to our alcohol carbon. They'll always have this same 3-carbon spacing. All right, so let's do another example here. I want you guys to connect these things correctly, right? We're going to give me my product of this aldol addition reaction. Okay, we're going to take butanone in the presence of sodium hydroxide. I lied. We're going to make this symmetric. It's going to be 3-pentanone. I need to connect the alpha carbon of one to my carbonyl carbon of the other. All right, we can note that since our nucleophile is reacting at its alpha carbon, not at its carbonyl group, that carbonyl group will remain intact in my product. And I'm going to draw my new bond here. Well, what must live on the other side of that new bond? The carbonyl carbon of my other molecule. All right, so now I have to draw in that oxygen as well as my carbons on either side. All right, and that carbonyl oxygen of my electrophile will become an alcohol in my product. All right, so this is our aldol addition product here. Okay, These reactions are often paired with a follow-up reaction. If we carried out this same process in the presence of heat, we wouldn't get the aldol addition product, but rather what they call the aldol condensation product. And what heat is going to do is we're going to get a dehydration reaction where we lose our alcohol group and replace it with a carbon-carbon double bond. All right? That carbon-carbon double bond is going to form in a very specific place. This alcohol is going to dehydrate in a very specific direction here. And that is going to be between our two new carbons, on our new carbon-carbon double bond here. So if we did our condensation product, we're going to draw in a carbon-carbon double bond between that nucleophilic alpha carbon and that electrophilic carbonyl carbon. And now we just got to include those additional carbons from my product. All right, so carrying out this same reaction, but in the presence of heat, would give us a aldol condensation product instead. All right, let's try to think, why does the double bond form in this specific location? Why doesn't our alcohol group dehydrate in a different direction? Let's say down here. Okay, so why would it dehydrate? Why is this one wrong here?
Less substituted?
So substitute is a really good guess, all right? And that is part of the correct answer here, is that this one is indeed more stable. And substitution was a big factor in stability, don't get me wrong. But there's something else that this thing has that makes it much more stable. Rewinding back to the very beginning of the course, what do we call that double bond, single bond, double bond spacing? Conjugation, right? So that double bond is going to form in that location, so it's conjugated to that carbonyl group as well. Okay? We're going to talk quite a bit about these products next lecture. These products that have this double bond right next to that carbonyl group, these are called enones. Cool. All right. So now we're going to talk about another reaction that is very, very similar to the aldol reactions, what's called a Claisen condensation. All right, this is like analogous to an aldol addition, but using an ester instead. Okay, so instead of taking an aldehyde or ketone, now I'm going to make an ester. And we're going to do the exact same thing where we add a little sodium hydroxide to our mixture here. All right, and I want to try to reason through what our product's going to be by looking at our mechanism. Okay, so in the same way, I need to draw not one, but two of my esters here. Because again, this is going to be a reaction between neighboring esters. All right, one of them is going to be my electrophile, and the other one will be my nucleophile in this reaction. All right, what's going to be the first step here? What was the first step in my aldol addition reaction? Close. We need to create our good this molecule will be our nucleophile, but we don't have a good nucleophilic site here yet, right? What do we have to do to create that good nucleophilic site? We got to take advantage of what's unique about this alpha carbon, the fact that it has that acidic hydrogen to it, right? So the first step is to deprotonate that alpha carbon. So I'm going to draw my hydrogen on here. And everybody's going to take a second and deprotonate that alpha carbon so we can create that good nucleophilic site. So by deprotonating that alpha carbon, now I have my good nucleophile. So my base just accepts that proton. So I have my good nucleophilic site here. We got a special name for this thing. What do we call it? On the board.
Enolate.
Enolate ion, right? That's our intermediate in these reactions here. Cool. These are our good nucleophiles that we create by deprotonating those alpha carbons. All right, so now we're going to have our nucleophilic attack. My nucleophilic pair of electrons is going to attack that electrophilic carbonyl carbon. As always, that kicks that pair of electrons up to create that tetrahedral intermediate. Okay, so this is where things get complicated here because I'm combining these two molecules together to make this new big ugly molecule here. All right, so I spaced it out since I'm going to have 4 bonds here. These are my carbons from my electrophiles, so we're going to keep that carbon in blue. When I draw my new carbon-carbon bond in my tetrahedral intermediate, on the other side has to be that nucleophilic alpha carbon. All right, so from there, I'm going to make sure to include, all right, here's my carbonyl carbon. Then I have my ester group, my ester substituent down here. All right, all this connected. Okay, again, everything's big and ugly. We want to make sure that we've tracked this correctly. So always a good idea to go and count carbons. Right, 1, 2, then I should have my oxygen, then that methyl group, all right, cool, 1, 2, then I should have my oxygen, then my methyl group, okay, cool, right? Make sure to sort of track where our carbons are going here. Well, especially when you're starting out, using colored pencils or whatever it may be can be super duper helpful. All right, so now we get this tetrahedral intermediate, and we've seen this intermediate a whole bunch here. And when we get our tetrahedral intermediate, what do we ask ourselves? Do we have a good leaving group? All right, so do we have a good leaving group here? All right, well, we don't have a good leaving group, that's for sure. We don't have anything great going on here. But we do indeed have a leaving group on this molecule. What's going to happen is this pair of electrons is going to come down and it's going to kick off. Carbon's never going to, carbon with the negative charge is super unhappy. It's going to kick off this oxygen here. All right, so we're going to get this alkoxide kicked off as a leaving group. All right, we're going to lose, and I'm going to keep that blue carbon there to indicate exactly what fragment I just lost here. Okay. So everybody take us, this is the product here. Everybody following our electron pushing arrows. Draw me the product of this reaction. All right, we'll talk about why it's a good leaving group here in a second, but let's make sure that we can just follow our arrows. So we're going to have reformed that carbonyl group. Keeping my coloring consistent here. This is from that electrophilic chunk. All right, now we have our, really just that whole intact ester there connected at that carbonyl carbon, or I'm sorry, alpha carbon. All right, my nucleophilic site. And my nucleophile didn't involve its carbonyl group at all, so that's also intact. And it didn't lose its ester substituent at all, so that's also attached. Okay, so here's our product of this reaction here. Okay. Before we go on, let me just note, we had this way of making sure that our product was connected to correctly when we did our aldol addition, right? If you remember, we start counting from our carbonyl carbon. We should always have this 3 carbon spacing from our functional group. I should have made a note here when we did our aldol addition. If we do the same thing, 1, 2, 3, notice again, our spacing holds up here, and in fact, our double bond in these aldol condensation products will always be between carbons 2 and 3. So again, kind of an easy double check to make sure that things are hooked up correctly. And if we look at our Claisen condensation product, again, we can do the same thing. All right, if we start counting between our carbonyl groups, we'll see they also have that same 3 carbon spacing. And that'll always be the case in your Claisen condensations. Okay? Cool. All right, so we said that we had this leaving group here. All right, so let's just talk about for a second why we lose that alkoxide. Right? Why does this reaction right here occur? Because we said oxygen is not a good leaving group. We've talked about that quite a bit. And we're producing this negatively charged alkoxide ion. All right, so how are we going to square those two away? This idea that oxygen's a bad leaving group, and yet we successfully kick off this oxide ion right here. Okay? So if we look, the devil's in the details here. All right? If we look at the bonds being made and bonds being broken business, we look at the energetics of these two. Both of these intermediates here, or rather both of these compounds, my reactant and product, has an oxygen with a negative charge. So yes, oxides aren't very favorable to form. I already had an oxide in my intermediate here. So that means that the delta H of this step equals 0. All right, if anything, it's actually probably favorable because carbonyl bonds are particularly strong, but nonetheless, right? From a bond sort of like how pissed off is this oxygen standpoint, we have a mad oxygen on both sides here, right? Oxygen with a negative charge, oxygen with a negative charge. So nothing really has changed there. What we gain, though, is the fact that we took this big, complicated molecule and we broke it up into these two smaller parts. All right, and it's probably been a minute since you've thought about this particular source of energy, but that means that the delta S of this step right here is positive, or it is entropically favorable, right? We take this big, complicated molecule and we're breaking it up into these two smaller parts. That's always something that would be entropically favorable. So from a how mad is the oxygen standpoint, things are pretty much a wash. And instead, you get you get more disorder out of there. You get two little parts floating around, right? Entropy is a measure of how much disorder is created in a process. The universe loves disorder. So this process here is entropically favorable because we took this big molecule and broke it up into two, right? So again, why does our oxygen play the role of a leaving group here? Kind of devil's in the details between these two steps. We already have that negatively charged oxygen. And the benefit of these two steps is getting these two fragments here. All right, so our Claisen condensation is very, very similar to our aldol until we get to that tetrahedral intermediate. Right? Previously, we got to our tetrahedral intermediate and we asked ourselves, is there a good leaving group? And the answer was no, so we protonated it. That's how we got that aldol product, that alcohol group of our aldol product. Here we form our tetrahedral intermediate and we ask ourselves, is there a good leaving group? And the answer is yes, right? So instead of forming an alcohol, we reform that carbonyl group, kicking off that ester substituent as a leaving group. All right? One more thing about the conditions in which this reaction is taking place. I lied to you a little bit by saying it was the exact same as an aldol because we don't use hydroxide. All right? Instead, we're going to be clever and we're going to use the base that matches our leaving group here. All right? So instead of using hydroxide, we would use an alkoxide. All right? And our solvent that we use will have matched that ester leaving group as well, that ester substituent as well. In this case, it's a 1-carbon group, so we would use methanol. All right? But our base and our alcohol will match that ester substituent. All right, remember hydroxide, if we had put that in there, instead we would have that saponification reaction and we would form a carboxylic acid. So we still need a base, but we're not going to use hydroxide. We're instead going to use an alkoxide ion that matches our ester substituent. Okay? Cool. So both Claisen condensations and our aldol addition condensation reactions, they have a base deprotonating that alpha carbon. That's the name of the game, is creating these enolate intermediates here. All right? It turns out that this base is not all that strong in comparison to how acidic our alpha hydrogens are. Only like 0.0001% of your molecules will ever be deprotonated at any given time. But because the design of these experiments, because I'm taking a beaker of ester or a beaker of ketone, I can just add base in there, and even if it's 0.001%, that 0.001% will react and will continue that process until eventually that reaction goes to completion, right? So this setup will work if we're talking about a pure sample of ester or aldehyde that we want to react with itself, okay? But what if we want to create these enolate ions and react them with some other electrophile? This base is not going to be strong enough to do it. Okay? It won't create a beaker that's 100% enolate ion, right? It's only going to create a very small fraction. So how do we create enolate ions? So we're just going to note hydroxide and alkoxides, those negatively charged oxygens, are not strong enough to efficiently deprotonate an alpha carbon. All right, so instead, if we really wanted to create an enolate, we would have to use a stronger base to do it. And there are two that we like. All right, and that's because they target different areas, different alpha carbons. Okay, so in this example here, now we have an asymmetric ketone. We have a secondary carbon, right? This is an alpha carbon over here is secondary, but I also have a primary alpha carbon over here. Okay, we're going to use a strong base, a super strong base, something even stronger than a hydroxide or an alkoxide. All right, we're going to use that sodium hydride that we've seen before. All right, anytime I see sodium, I'm like, that thing's not doing anything. I erase it and replace it with a negative charge. That's my real base here, this hydride ion. And this is about as teeny tiny as you could possibly get of a base, right? A single hydrogen atom ion with an extra pair of electrons, or with an extra electron, is incredibly tiny. We sort of make this even more drastic by carrying this out at higher temperatures. All right, and what that teeny tiny base at high temperatures is going to do is favor deprotonating that more substituted carbon. This would be my thermodynamic product. The more substituted of those two possibilities is going to be the one, it forms the most stable enolate ion. You can see this more easily by looking at the other resonance structure and convincing yourself that it has that more substituted double bond. All right, so at high temperatures, with sodium hydride, we'll deprotonate that more substituted alpha carbon. We can use another base, LDA. All right, and LDA is an amide ion, a nitrogen with a negative charge. But it's got these two big, bulky groups on there. There might even be a branch point here, I don't remember. Anyways, it's got these two giant alkyl groups on here. So LDA is a large base, as opposed to sodium hydride, which is a small base. And again, we make this even more drastic by carrying this out instead at low temperatures. And so instead, what's going to be preferred is the kinetic product. Since that LDA is so large, it can't access that more crowded secondary carbon. So instead, with this base here, we're going to end up deprotonating that primary carbon. Let me make this smaller. All right, or our less substituted carbon. All right, so just to summarize here, the sodium hydride at high temperatures that will deprotonate the more substituted carbon. If we instead do LDA at low temperatures, that will deprotonate the less substituted carbon. All right, and that's how we can create a sample of pure enolate ion, a good nucleophile that then we can take and turn around and react with other electrophiles. Okay, so let's look at an example here. Let's take that butanone. All right, we're going to split it up. And in the first, we're going to add sodium hydride at high temperatures, followed up with our electrophile here. One bromopentane. And in our other sample, we're going to take that same butanone, but use it in LDA at low temperatures, and then add in that same electrophile. All right, so these reactions are called alpha carbon alkylation reactions, where we take an enolate plus an alkyl halide okay. Our difference here is exactly where that enolate ion forms. If we use our sodium hydride at high temperatures, it'll form on that more substituted carbon. And if we use our LDA at low temperatures, it'll form on that less substituted carbon. All right, that carbon is just a nucleophile. Where's the electrophilic site in this alkyl halide here? Yeah, the one that's attached to the bromine, so boom, boom. All right, these were your first electrophiles that you were introduced to in organic chemistry. So I know everybody's like, yeah, no, I know them well. All right. And we can see our byproduct here. What's going to happen is we're going to alkylate that particular site. Okay, so in the case of our sodium hydride, we've added 3 carbons to this alpha carbon. In the case of our LDA, we've added 3 carbons, and I'll keep my coloring consistent here, to our other alpha carbon. All right, sort of as mentioned before, counting carbons are going to be super helpful, so we should just convince ourselves real quick We have 4 carbons from our nucleophile and our 3 carbons from our electrophile. All right, those electrophilic carbons are just attached to a different alpha carbon depending on what base we use. Okay, so it's what we would call an alkylation reaction, adding an alkyl group. Okay, we can also use this strategy to create aldols, but what we would call mixed aldols. All right, so let's do our same butanone we could just add sodium hydroxide and do an aldol reaction, but it would be reacting with itself, right? What if instead I wanted to react it with a different aldehyde or ketone? So what if I just wanted to use propanal? That's why this would be a mixed aldol reaction. All right, and again, first I'll try this out with sodium hydride at high temperatures. Then I'm going to do it with LDA at low temperatures. All right, we will have to have some protonation step after this as well, because it's an aldol, we won't have a good leaving group, and we'll just have to protonate that. All right, so everybody take a second and see if you can't figure out what our aldol addition product's going to be here. So again, our key difference here is where we've deprotonated. Our secondary alpha carbon or our primary alpha carbon. All right, and now we got to put together what we know about our aldol addition reactions, where that carbonyl, or rather where that alpha carbon attacks that electrophilic carbonyl carbon. So when I draw my product here, I have my nucleophilic secondary carbon. My new bond here is going to be to that carbonyl carbon of my electrophile. All right, after that first step, we get this alkoxide ion, but again, we don't have a good leaving group, so when we do that last step, we will have protonated that oxygen. And again, we can tell that this is drawn correctly by looking at the spacing of those two functional groups. All right, so if you've not already, apply that same logic to our other enolate ion over here. That alpha carbon is going to attack the carbonyl carbon of our aldehyde or ketone and create that new carbon-carbon bond. My carbonyl oxygen will become a hydroxyl group. All right, and then just real quick, just to note, because we did have both aldol additions and aldol condensations, the only difference being if I had given you this exact same problem, but said also we're going to include some heat in there. All right, instead of my addition products, oops. I'm going to get a carbon-carbon double bond that is conjugated to my carbonyl group. Let me clean this up. All right, so let's take this addition product and turn it into the condensation product for me. So again, I'm going to dehydrate, and where is that double bond going to go? Conjugated to my carbonyl group. All right, so we can use enolates with other electrophiles. In particular, we've seen alkyl halides, we've seen aldehydes and ketones, these mixed aldol reactions, and then lastly, this other electrophile we saw today, these mixed Claisen reactions. All right, so now let's take our same setup here. We'll keep our butanone the same. But now instead of an aldehyde or ketone, we're going to be adding in an ester. right, so again, the difference here being which alpha carbon gets deprotonated. This direction would be my green. This direction would be my orange. Okay, we're going to get something very similar to what we saw with our aldol addition, except that when that tetrahedral intermediate forms, it's got that good leaving group that it can kick off. And so that's exactly what happens. We lose that leaving group and we reform our carbonyl group. All right, so I've added these 1, 2 carbons on to my alpha carbon. And again, I have my same 3 carbon spacing that I always have. All right, so the aldol versus the clayson, the only difference is what happens at that tetrahedral intermediate. In an aldol, you're stuck and you just have to deprotonate it, or you just have to protonate it, getting an alcohol group. With a clayson, you have that built-in ester leaving group there, and that can play the role of a leaving group, allowing you to reform that carbonyl bond. All right, with this one, we do the same thing, but it's just over on the other alpha carbon. Again, giving us our same 3 carbon spacing. Right, so these aldol reactions, these clayson reactions, and then these enolate reactions, you really want to think about them from the mechanism standpoint because they're all sort of saying the same thing over and over and over again. If you can understand the mechanism, it's going to be much easier to figure out what's going on. Just trying to figure it out based on patterns is going to be much harder to do than with other reactions because you're creating these big, ugly molecules on the product side. So thinking about the mechanism and how these things get connected is going to be really important to understanding these reactions. We got one more lecture to go, and then you're done.